So last time we introduced this notion of a runtime facility for allocating memory that is not the stack, okay? Because we found that the stack works really well with certain kind of usage patterns, particularly function calls. We're really great with function calls and using the stack, but anytime we have other circumstances that don't really fit with that pattern, we would like to have another facility. And so we introduced this notion of the heap, where we can say, give me some number of bytes, and it gives you back a chunk of bytes. Or it might say I can't. Remember, that's an option as well. And when we're done using the bytes, then we have to go and tell it with free, hey, I'm done using these bytes. Otherwise, we have a memory leak. Okay. I'm going to talk about this. You can see the details for arrays. We already talked about it. The whole concept of a memory leak is that your program no longer has any reference to the resource, and the system still thinks it's in use. So you're both screwed, right? Because you can't ever tell the system you're done using it, okay? And the system can never figure out that you're done using it. And so that's the problem with a memory leak. Okay, that's why we call it a leak. There's a lot of other things you can leak as well, and it's always exciting and fun when you encounter those kinds of situations. But anyway, we're going to try to avoid leaks. That's the big benefit of using valgrind, is it will tell you when you're leaking things, usually. You can probably tell I didn't run valgrind on homework 1 code that I gave you, so I will fix those bugs for next year. But anyway, the question that we had started to tackle was how to implement this particular function in x86-64 assembly code. Really simple, right? We take two vectors, they have a length, we're supposed to heap allocate a new chunk of memory, the same number of elements, and compute the sum into that and then return it. How hard could that be? Now, the code example that we're going to go through is for 64-bit Linux. OS X is a giant pain in the butt to do this with, so we will not be looking at how OS X does this, but you could take this and run it through GCC-S and see what it produces. Okay? So it's not like it's that hard. The real difficulty here is primarily in calling malloc, because everything that OS X does is dynamically linked, okay? And so you need to set up a stub and call it properly, and it's just a bunch of annoyance. Okay, first question. It's always good to start with the arguments and the return value. So, using the convention, it's the longest convention name ever, right? System 5 AMD 64 ABI, okay? Where are the arguments going to be? Do we have more than 6 of them? Thankfully, no, right? So where will they be? Registers of some specification, right? So what is it? RDI, RSI, am I guessing right? RDX, something, something, something. Those are all the ones that we need for right now, so RDI. Now here's an important detail. A is a pointer. And we know that pointers in 64-bit C are going to be 64 bits, even though we already talked about how the processor only cares about the low 48 bits. We're not talking about that. The pointer is still 64 bits, so that means it'll be in RDI. B will be in RSI. And now length is an int, so where will length be? Remember, it'll be in EDX because it's 32 bits. Not 64 bits, okay? Now, if everything is wonderful in the world, then maybe the top 4 bytes will also be 0. That would be really awesome. I don't remember if that's the case or not, but thankfully we kind of don't care because we're only going to be using the low 32 bits throughout our entire implementation. Look, we never use length as a pointer. We never use length as an index into something else, so really, we can get away with just using EDX. And I'm telling you that up front so that we don't worry. Okay? So what I love to do when I implement assembly code, and I strongly encourage you to do this, is write a little outline for what it is you need to do, and always put these specific placeholders into that outline. First of all, I always have a comment header at the top, and this is actually a really abbreviated comment header because I don't have a lot of space on the slide. Normally, I would say this function is supposed to take two pointers to vectors and the length of those vectors and add them together. I would probably have the C-style declaration so that I know what the types are. Because guess what? Assembly code doesn't really have types. You'll see that as we go through this. And but at a minimum, you need to know where the arguments are. So A is an RDI, B is an RSI, length is an EDX. Okay, so we know what we're dealing with. And then I might need a stack frame. I might need to save callee save registers. Please find a seat. Don't just stand in the door. You're going to make me nervous. Then we need to allocate space. Remember, allocating space was part of what our C code did. Then we need to implement the loop. And then we need to undo our saving of registers, and we need to restore our frame, okay, to whatever the caller's frame was. Okay? So these are the steps that we may need, and since we know we're always going to be doing these steps, or we may need to do these steps, why not throw comments in there, and that'll remind us where we are in the coding. Okay? But you can see at least we have one instruction, right? We know we need to go back to whoever called us, so we have the ret Q at the bottom. Okay, now here's a guess. We only have 3 arguments. We know that they're going to be passed in registers. We know we have 16 registers to use, and our function doesn't have a whole lot of state. So I am going to assert that we won't need a stack frame. Now, just to make sure that we're all on the same page, I'm going to go back to the code, and let's look at the code really quickly. What kind of internal state is this function going to need? Okay, we know that we have A, B, and length. We know we need to return a result because that's at the bottom. Result is returned in RAX, so we know we're using RAX for something, right? And then we have I, we have a loop variable. Okay, so we'll need a register for that. What else? Maybe to do our summation, right? Because we're reading 2 memory locations and we're saving that into another memory location. And we know we can't do that all in one step. So maybe another register. So already you can see that we're not anywhere near running out of registers. So that's why I can eyeball this code and say, I think we're probably okay as far as not needing a frame. Okay? So why set one up? Okay, everybody agree? Everybody also convinced? I hope so. I think that there's very few functions in this class that require frames. In fact, there may be none. It's just like, this is the beauty of x86-64, is it just kind of obviates the need for having stack frames, which is really great. It makes your code simpler. Okay, now we need to call malloc. Again, we have this one simple line of code in C. How would we actually implement this in assembly code? Okay. Well, malloc also uses the same calling convention, except now our function is not the callee anymore. I mean, it's still the callee, but now it's the caller of malloc. So it needs to treat malloc in the same way it wants to be treated. It needs to follow the convention. Okay, so malloc has one argument. Where will the argument be? RDI, hopefully, right? So that's going to be where malloc's argument is. Where's the return value of malloc going to be? You guys are kind of leaving me hanging here. RAX, right? Yeah? So, and the neat thing is notice result equals malloc. We know that'll be an RAX, and then we're going to return result anyway. So, why not just leave that in RAX? Okay. Now, by the way, you may notice something. I hope this is grading on at least a few of you, because that's important for systems programming. I don't check the return value of malloc. I should. If I were writing nice, safe code, I would. But in this case, we kind of assume all the way up to like lab 6 that all allocations succeed. So it's a nice simplifying assumption. But you would never want to do this in real life. Okay? So we're going to go ahead and take length. Now, what size of int? I have it on the slide already, and we've talked about this previously in class. Ints in 64-bit are still 4 bytes. In general. So, you know, it may be a platform that's not true for, but at least for x86-64 in C, we know that ints are still 4 bytes. So we take length, multiply it by 4. There's an easy way of doing that, right? Shift it left 2 bits, so then we have that part taken care of. We invoke malloc, and then magically there's something going to be in RAX when malloc returns. Okay? Okay, so that's pretty easy so far. Here is some assembly code that may actually do what we want. Okay, so notice we have A in RDI already, because that's how the caller passed A to us. But we'd like to keep that around. We need to use that to invoke malloc, so we save RDI. And then we move EDX into EDI. Remember that this is the length, and the length is an int, so it's only the low 32 bits. So we move that into EDI. That has the nice benefit of 0 extending into all of RDI. We shift it left 2 bits. That multiplies it by 4. And then we call malloc. And that's all we have to do. Now, magically in RAX, well, RAX will either contain a pointer to our memory or it will be null because something went bad. Okay? But we're going to assume that everything worked fine. Any questions? Yes? So what is passed to malloc is the number of bytes that I would like. So basically the whole, how shall we say, the contract with malloc is that I tell it how many bytes I want, and it either gives me back a pointer to a chunk of memory that's at least that size, or it gives me back null, saying I couldn't find that. Okay? Yeah. Yeah, you.
How do you tell the linker which malloc?
So that's a really kind of a much deeper question. This, when you run this code through the assembler, it doesn't make any assumptions about what you mean about malloc. All the object file says is, hey, there's some symbol named malloc, and you tried, invoking it through a call. That's all the object file really says, and so it's at link time that you would say, use this malloc. Okay, so that will get patched at link time. Another question? So this is a really interesting question. If you didn't care about saving the value of A, would you have to push and pop RDI? The answer is no. Okay? But this does prompt another question that we should be asking ourselves, which is, are there any other registers that malloc may have its way with? Are there other call or save registers that we might want to preserve that malloc may trample on? Was there a comment over here? Yeah. Yeah, RSI would be another one. What's another one?
RDX.
Yeah, RDX. We may want to save all of those. Yeesh, right? So we need to make sure that we actually preserve those as well. Okay? So this is where you have to be careful in your analysis. And I'm going to give you a big giant hint because I like you all and want you to get sleep next week. Think about this issue because some of the code that I give you calls malloc, and you need to think about how it interacts with malloc. Okay? That's a big giant hint for part of assignment 3. Okay? So you can see here that since malloc may change registers, we may also want to, in fact we really do want to, save RSI and EDX because we care about both of those. Now, the comment was we need to save RDX, and that's absolutely correct because we can't just push EDX. The x86-64 ISA doesn't allow us to. We have to push 8-byte values if we're in 64-bit mode. Okay? So that's just kind of a rule. So this might be what we end up with at the end of making our allocation code correct. Okay, notice we save our registers we care about. We set up the arguments in RDI. Move EDX into EDI, that 0 extends into RDI. We shift it left 2 bits so that we can multiply by 4. We invoke malloc. The answer comes back in RAX. We assume everything's hunky-dory. Okay, then we restore the registers we care about. Okay, make sense? Yes?
The length passed to malloc, is it how many bits it should allocate? Because when we call it in C, for example, we have to specify a number and a type of variable.
So in C, we don't actually have to say what type of thing we want to allocate, which is scary. Like, this is the reason why people don't like C very much. You just say, this is how many bytes I want. And then it's up to you to take that pointer and cast it into the appropriate type so that you can then work with it properly. Okay? Now, you'll notice that most of the time when you invoke malloc, in C, you say blah, blah, blah times size of some type. That size of some type does nothing to malloc to tell it what kind of thing you're allocating. Malloc is very simple. It just says, this is how many bytes they want. I'm going to go find a chunk of memory and return. You guys remember the type that's returned by malloc? Void star, right? So void star is an untyped pointer. It's up to us to decide how to treat it. Okay? This is why people talk about C being a low-level language. It's not really. I mean, seriously, C is pretty amazing compared to what existed before C was created. Okay? C was a giant step toward having more platform-independent code, and obviously many more steps were necessary. But that's one of the characteristics of malloc, is that you just tell it how many bytes and it gives you back a pointer. All right, any other questions? All right, good questions though. These are exciting. So now we have the first line of our C code implemented, right? We have a whole bunch of assembly instructions to implement our first line of C code. Now we need to do our loop. We need a loop variable, and so this is where you just pick something, and I would strongly encourage you to pick something that's call or save so it's not your problem, right? Make your code simpler. So in this case, I picked ECX. Why? Because, you know. And you'll notice here that, how do we use I? Well, it's an int, so that's why I said ECX. We increment it. That's not a big deal. But then we also use it for indexing, right? Since we use it for indexing, it's going to be part of that whole crazy reg B, reg I, scale thing. And remember that those registers that we use with the base and the index, they have to be 64-bit. So when I say we're using ECX, well, implicitly in your head you can say, oh, okay, I'm using ECX, that's what I'm focusing on, but RCX is going to be important too. Okay? So again, I want you to think about these things as we go through the implementation. Okay? So need to access element I of the arrays. So we'll use something like this. Remember, what is our pointer to A in? Well, it's in RDI, so we know RDI will be one of our bases. B is one of our arrays, and that'll be in RSI, so we'll use that as one of our bases. And the result, if malloc succeeded, is going to be in RAX, so RAX is going to be one of our bases as well. And RI can just be RCX everywhere. Okay? Everybody with me? So hopefully, pretty straightforward. Now, we're going to not show you all the steps, and that makes me a little bit sad. When I was going through the lecture this morning, I was a little bit sad, because remember, last lecture we talked about for loops, and we said for loops are initialization, and then a while loop, and the update code is at the end of the while loop. And that's all it is. And so ideally, we would go through those steps of translation. Okay, that's the practice you should get into, but I'm not going to do that because it's a really simple loop anyway. Remember, we said for I is 0, and we said that ECX is going to be our loop variable I, so the first thing I'll do is I'll just set ECX to 0. Now note the comment. This is the kind of thing that's really great to put in your assembly comments if you're trying to figure out an appropriate amount of commenting. I set ECX to 0, that means all of RCX is now 0. Because x86-64 always 0 extends 32-bit writes to low registers. Okay. Okay, so now I'm going to throw a bunch of code up here. We'll have to talk about it. Remember that a for loop is a while loop, and we take a while loop and we peel off the first comparison and just skip over the entire thing so that we can turn the rest of the loop into a do loop, because do loops are easy to code and don't require a lot of jumping. Okay, so that's exactly what we've done here. We've said for I is 0, so that's the move L0 into ECX. We do the first test. Is I greater than or equal to length? If it is, jump over the whole thing. So if somebody invoked our function and said, here's a pointer and here's another pointer, and by the way, my length is 0, I'll just skip the entire loop. Okay? Otherwise, if that's not the case, then I know I have to go through at least one time, so I can jump into my do loop now and just start doing stuff. And so you can see move RDI RCX4. That's A sub I. Okay, I'm working with ints, so those are 4 bytes, and RDI points to A, so then RCX is the index. Okay, so I move that into R8D. Then I add in whatever B sub I is, and then I take that computed value and store it into result sub I. Okay, everybody got the code for VAD loop. This is really important I'm going to tell you that sometimes I give out midterm exams and then I cry a little bit because students forget that you have to think carefully about the size of the element you're working with when you're accessing arrays. If I give you an array of bytes, you won't have the comma 4 on there. It'll mess everything up. If I give you an array of longs or whatever, then that will be 8. Okay, so you have to think about these details when you implement your array access code. And I just want to say that now because sometimes midterm problems make me sad, or I should say midterm answers make me sad. Okay, anyway, so ECX is I. We finish our result I equals AI plus BI. We increment ECX, so add 1 to I. And then we do our subsequent for loop tests at the end. Again, we see, has I passed length yet? If not, jump back to the top. Implicitly, we're saying, if so, fall through. Okay? And that's our entire for loop. Any questions? Yes?
So, random question. So, we have this for here that is just for. When we write code in most languages, we are asked to not have magic numbers around the code, to have some variables set to them.
Sure.
We wouldn't do that here. Like, we wouldn't set, like, size of int equals 4 and then call size of int or something like that, right?
The thing is that we're pretending to be the compiler. Your concern about magic numbers is great, and if you were to have any other magic number, like you always knew your vectors were going to be 10 elements or something, that would be the kind of thing you'd want to have a definition somewhere, saying, my vectors are always 10. Okay, so that's really great. The thing is that there's certain things that we kind of assume in assembly programming, and one of them is the size of ints and sizes of longs and so forth. And the other aspect of this is that it's not really possible to put something else into that code unless you start getting the C preprocessor involved, and it gets really gross, and I don't want to even show you it's possible because I don't want you to ever do it again. Okay, so there's things like that. And so since we're pretending to be the compiler right now, we're just going to say, yeah, ints are 4 bytes, longs are 8 bytes, characters are 1 byte. And so we'll just write the code assuming that that is the case. And so one could look at this as a bad behavior, but generally it's widely accepted behavior when you're writing assembly code. I hope that answers your question. All right, anything else? Okay. Wow, I'm very popular right now. Okay, conditions. Pain in the butt. And I mentioned this last time, or maybe a couple times ago, that AT&T syntax, I love it. I'm in love with AT&T syntax, except for one dang thing, which is dealing with comparisons. And so I just wanted to show you this code. Since we have I is less than length, this is the comparison that we're doing. Here are the conditions that I wrote. Okay? You'll notice that I say, is I less than length, or is I greater than or equal to length? Well, the way that I wrote it in the assembly code is to actually reverse those arguments. Notice length comes first and then I. So I flipped it. Why did I flip it in the assembly code? Well, the main reason I flip it in the assembly code is so that I don't have to flip it in my comments. So it's the same way as the C function so that I understand what I'm doing. Okay? So that's the reason for that. And it ends up giving you pretty natural conditional jump instructions after that. Okay? So compare length and I. Notice I flipped them, and then I can just say, okay, what I'm really checking for is to see if I is greater than or equal to length. Therefore, I have JGE, jump if greater or equal. Okay? Same thing at the bottom. Compare length and I. Yes, my condition is I less than length, but I say length and I so that I can say jump if less than back to the top. Okay? So that's the one magic trick that you really kind of need to pay attention to. When I do comparisons with CMP, I flip the arguments so that I can match my pseudocode. Okay? You can certainly have the arguments the other direction, but now you're going to be writing something else for those jump instructions. Okay? Any questions? All right, that's the one annoyance that you run into with AT&T syntax. I'm sure there's others, but that's the one that we'll run into. Okay, so we need to basically look at, remember we have our to-dos, and one of the to-dos was, do we have any callee save registers? Well, guess what? Do we have any callee save registers? We carefully avoided the callee save registers. We didn't set up a frame. We didn't need a frame. We didn't touch RBX because why? I mean, that's why we used RCX instead. And we definitely didn't touch R12 through R15. We touched R8. Okay? So that means that we're actually done with that. Okay? Yay! The best code in the world is code you don't have to write. Okay? The second best code in the world is code you don't have to execute. But this is definitely the best code. Okay? So we end up with our implementation like this. So notice the first part of it, all we really do, since malloc is the only thing that demolishes registers we might care about, we save our register values before invoking malloc. We invoke malloc, we pop those registers, and then we do our vector sum loop. Okay? Are there any questions? One thing that I will mention here, and because sometimes it bewilders students, are there any types in this assembly code? Sadly, no. Hopefully we're all crying a single tear. This is one of the things about assembly code. In languages above the processor, you have a lot of type stuff. And in fact, if you have a really nice language, it may do a lot of type checking to make sure you aren't being an idiot. This is the problem with writing stuff in assembly, is that there's nothing keeping you from being an idiot. Okay? You want to have an int and you happen to use a 64-bit register and there's stuff in the top 32 bits, then you're sad. It's broken, right? Or you have some string you're reading and you take some characters and you try to treat them as a pointer. Nothing will stop you at this level. Okay? So you have to pay attention. And that's why assembly code is a little bit hard to write. Okay? So I just want to point that out because you do run into these kinds of situations from time to time. Hopefully stuff is simple enough in this class so you won't run into it like really badly. Okay? But these are the things, like our vector add loop. You know, we have to keep in mind, oh, I'm adding ints, so I need to go ahead and have 4 as the scale for doing my based indexed addressing. Okay, any questions? All right, well, so let's take this code and pretend we've saved it into vectoradd.s, which you certainly can type into a file if you have tons of time and nothing else to do. If we want to call this function from outside this assembly file, we need to use that .global directive because that tells the assembler to make vector add a public symbol in the object file that it generates. Okay? There's a lot of, remember that whole the size of this thing is blah, 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 and this is a function, and we could just, jump through all the hoops. You can align it so that it's super fast to call and just make it amazing, but you don't need all that. You just need that .global thing. Okay? And then you can assemble it. So you run it through the assembler. You have to tell it what output file to create. Does anybody know what the name of the file will be if you don't say the -o line? Yeah, a.out. Thank you, assembler. You made an assembly output file. That was really helpful. Anyway, so you can do that, and you can even do -g on the assembler to get debug information if you expect you might have bugs and may want to step into it with GDB. Okay, so that can be really helpful. In fact, I think most of the make files we give you from here on out will have -g turned on so that you can just trust that you can start it up in the debugger. Okay, so you do this, you get a vector add.o. You need some code that invokes it, so I just threw together something silly. Okay, we have 2 vectors of 5 elements each, and we allocate into res by invoking vector add, and then we print out the results. Okay? How hard is that? So we compile that as well, and then we can link these things together. Now, this is where if you had some fancy pants kind of malloc that you wanted to use, you could put it in on the last line where you're linking it all together into an executable. But since we're not saying anything, it just uses the C standard library, and it links that in so that it will invoke malloc. Okay? You run it, and of course, because this all exists entirely in a slide, it works. Yay! I actually have run this, and it does work, but anyway, pretty straightforward. Any questions? Yes? You want me to go back?
Yeah.
Okay.
Like, I
Yeah. You don't need extern in this circumstance because extern is really most important for state values that may be accessed from another compilation unit. Okay? In this case, since it's a function, the compiler's a little bit more relaxed about dealing with those symbols. But extern is frequently used if you want to access global variables that are declared in another file. Okay? You may be able to say extern here, but it doesn't really make any difference. Okay, any other questions? We definitely don't want to say it's static because then it'll make that symbol local. It won't be visible. Okay, so enough of that. This is the kind of thing you'll get to play with starting in assignment. Well, I mean, you're already doing some of that in assignment 2, but in assignment 3, you'll get to see this more and more. So you'll get a few more weeks of fun, hopefully fun and exciting assembly programming. There's some pretty amazing things you can do. Okay. So hooray, let's look at how cool we are. We use scaled indexed memory access to implement this code, and it was really easy because the processor does so many things for us. I mean, we're not even talking about a load store architecture, forget about it. We can just stuff the base addresses and indexes into registers, and then off we go. Okay? We called a C standard library function by following the calling convention. Yay for us. And we return something that's much larger than a register to our caller by allocating memory and returning a pointer to it. Okay? So go us. We've already jumped, massively ahead as far as our capability of implementing things from a few lectures ago. All right? Now we had this other program that we were talking about. Finding primes. And we had this function, remember what it does is you give it n, and it tries to find all the prime numbers between 2 and n. Okay? Now, since we know the size of the result depends on the inputs, and we also know that there's not a specific way of computing how many primes we're going to find. You probably know that there's various ways of computing maybe an upper bound on that or something like that, like what's approximately what we might expect. But there's nothing that says this is exactly how many prime numbers you'll find between 2 and n. So we kind of need to build that up as we go. Okay? And so maybe we'll use a linked list. Everybody here confident with linked lists? Hopefully? Yay. Okay, good. This simple example, right? We have a value, and then we have a pointer to the next node in the list. And so we can just string these things together and have find primes return, let's say, the head of the list, so that you can just chase through and find all the prime numbers that were found. Okay? Here's an algorithm. We're not being fancy. We're not being sophisticated. We're just saying, hey, just look at each number. Notice, we don't even care if it's even or not. I mean, we're going to look at 4, 6, 8, 10, 12. We know those aren't prime. We're looking at them anyway. Okay? So we just say, if it's prime, add it to the list. We know this will work. Okay? So we're going to need a couple pointers in our little find primes function. We'll have one that's result. That'll be the head of the list. And then we have last, which is the last node we've allocated, so that we can just tack the next one onto the last node really easily. Right? Just last arrow next equals blah, 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 blah. Right? So we do that. Okay, and we'll use malloc to allocate the other stuff. So here's how we could do this. Notice we have int list star new, and basically we can say, if this thing is prime, then I need to allocate a new node. So I will use new to allocate that thing. Observant C programmers may notice, well, you could declare that int list star inside the if body, and that's certainly true. I have to try to fit code onto slides, and it's just really frustrating. It makes code a little bit less intuitive to write. But anyway, you say new equals, and then you malloc. And notice again, we're just saying, hey, malloc, I need this many bytes. And malloc says, sure, here's an untyped pointer. And then we just cast it to int list star. So now I can work with it as if it were a pointer to an int list. And I say, here's the value. It's prime. And new arrow next is null. Okay, so I create a new node. Then I have to figure out where I want to stuff that node. If last is set to something, then I know I have a previously allocated node, so I can say last arrow next is the new node. Otherwise, I don't, so result was null as well. I could assert that if I wanted to, but I'm going to say result is the new node because it's the first one I'm allocating. Okay. And then I go ahead and say, now the new node becomes the last node I allocated, and I'll just keep going until I find the next prime. Any questions? Hopefully all of you could write this code quite easily. Maybe not, bug-free on the very first time, but that's okay. That's a rare thing. Okay. So we do this. Here's the thing I want you to think about. How would we even go about building such a data structure on the stack? Nodes allocated and strung together. Like, how would we do a tree? Or how would we do a try? Or how would we do skip lists? Or all kinds of other really awesome data structures that involve all kinds of things being allocated and pointers to them. Okay? We can't do that on the stack. And so this is kind of a neat observation because it gives us another reason why we love the heap. Okay? The heap is better than the stack if you're trying to build a complicated data structure. Okay? So these were our previous reasons why we might use the heap instead of the stack. So the size of the result depends on the value of the input. Okay, we know the heap is really great at that. We need a result to live beyond the lifetime of the procedure. We know heaps are great at that. So a new reason is that we may have a data structure that just can't be represented on the stack without really doing something nasty. Okay? So there's 3 reasons why you might use the heap instead of the stack. Questions? Alrighty. So, where do these things live? We're going to talk briefly about this, and we're going to talk about it at a really high-level, hand-wavy way right now, because we're not going to talk about this until we get into like week 7, week 8 of the class. So where does the program itself live? Every program has a certain memory layout. Okay? And it turns out that they all follow the same pattern because that makes it easier to construct systems. So every operating system has a specific way that it lays out its programs. Okay? And so you have a region of memory for the stack, another region for the heap, blah, blah, blah. Okay? And some of these regions will vary in size. Okay? Like how big the program text is. Well, that clearly varies from program to program. What read-only data do I have? That also varies from program to program. So the compiler figures that stuff out, and the linker also has a giant role to play in figuring out those details. Some regions can't be figured out at compile time. Like, how big of a stack do I need? Well, that depends on the inputs as well, right? How big of a heap do I need? Same thing. Okay? So some of these things the operating system is responsible for managing. So here's a typical layout. Okay? Not to scale. So, and again, as usual, the high address is at the top, low address is at the bottom. But we have instructions, and then we have read-only initialized data, and then we have read-write initialized data, and then we have uninitialized data. So this is all your global variables. Hopefully those are tiny, right? And then we have heap, and it grows upward. Now somewhere way high in memory, we have the stack, and it grows downward. And the idea is that that'll maximize the amount of time before they meet, because if they meet, your program dies. Okay? We just run out of space. And then you have kernel stuff, like what is that? Why is that there? Well, we'll talk about that in the future as well. Okay. So blah, 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 blah. All of these things that I just explained. Okay, any questions? So this is what is happening when you compile your program and then you run it. You know, the OS is taking care of a lot of things for us. It turns out that this is also part of the application binary interface. The OS specifies the application binary interface, like how things should be laid out, and then the compiler is responsible for following it so that when you get your little binary and you run it, it actually runs. Okay? Okay, now there are variable size memory areas. You'll notice the stack, it grows downward. What if I have infinite recursion? Cool band name, by the way, but if you have infinite recursion, well, so the way that the OS figures this out is it says there's a limit on how big your stack can grow. If you grow beyond it, you're probably being naughty, so we're going to stop you. Okay? Same thing with the heap. What if you have a problem with allocating too much memory? Just can't get enough. So you allocate, and the OS finally says, that's it. I don't trust you anymore. Stop. Okay? So the nice thing is that you can tell the OS, actually give my program more stack because I use a lot. Okay? You can tell it things like that. Most of the time we don't have to, though. The limits are reasonably chosen. Okay? So there's a couple of ways that we can specify these things, which I'm not going to go into right now. But there's various ways that you can set these limits and how they're utilized. Okay? Not the point of the lecture, so we're going to skip that for now. Stack is easy. Remember that the compiler is what handles stack management. Okay? So it's just a memory region, our trusty RSP. We update that as we run. Okay? Yes, question?
So when we install a program on our computer like MATLAB or something like that, and it says that it needs 2 gigabytes, let's say, then a big part of that might just be the part of memory that is allocated for its stack and heap too.
Yeah, so if you have a program like MATLAB that says, I really would love 2 gigs of memory, there's a number of things going on there, but we'll just simplify it for now. This would be a great question to revisit in weeks 8 and 9. But what it's basically saying is, I'd love to have enough space that I can allocate up to 2 gigs on the heap. Typically, that's what it's saying. Programs don't use the stack as much as you might expect. Kind of a surprise. But anyway, yeah, so it would be saying, I'd love to have enough physical memory that I can have a heap that large so that I can allocate stuff. Okay? Now, getting back to the discussion, the heap is a complicated beast. And you will see that as you get into its implementation. So we have this thing called a heap allocator, which manages the chunk of memory and says when you give a request, I'd like this many bytes, it says, yes, here you go, or it says, sorry, I don't have that. So it's managing that resource. Okay. Now there's 2 kinds of heap allocators. There are explicit allocators. Explicit allocators require programs to explicitly free memory when they're done. They also frequently lead to cursing, but I don't know that that was the point of the name. You also have implicit allocators. Implicit allocators figure out for themselves when you're done using memory. So you can imagine that implicit allocators make it easier to avoid certain kinds of bugs, like memory leaks especially, right? Also, double freeze and things like that would be unnecessary to even have if you have an implicit allocator. Okay, so those use garbage collection. So we're going to start looking at explicit allocators today. What we're going to do in week 3 is implement an explicit allocator, and then week 4 you'll get to implement an implicit allocator. It's like my favorite lab of all time. So you should have a lot of fun with that. It's actually really cool. Okay, first thing. We don't know what sequence of allocation requests we will get. The program can ask for memory in any order it wants. So let's say that we had a monstrously huge 6 kilobyte heap, and we have these 4 allocations. 1 kilobyte, 1 kilobyte, 2 kilobytes, and then 1 kilobyte. And we just hand it out wherever we can fit it in. And then the program frees the second allocation. How much memory do we have available? 2 kilobytes, right? What's the largest allocation request we can satisfy? Not 2, right? People who are saying 1 are absolutely right. Okay? So we have available 2 kilobytes, but it's not contiguous. And so this is called fragmentation. Okay? Fragmentation is a situation where, based on the sequence of allocations and deallocations, the available memory is not contiguous, and so we can't hand out requests beyond a certain size. Okay? So this is really annoying. And it doesn't matter what strategy you choose, you can find a way to circumvent it by choosing an appropriate sequence of allocations to defeat that strategy. Okay? Kind of annoying. Okay? Once you've handed out a block of memory, you're not allowed to change it anymore. Okay? Part of the reason why is because we're talking about languages like C. They've got pointers and junk, and we may have a pointer into the middle of that thing. We may have pointers in that thing to other things. Okay? So what I mean by pointing out this detail is we can't slide C and D in memory to make this memory contiguous. This is a problem of explicit allocators. Okay? Once we've handed over a chunk of memory to the C program, for example, or the C++ program, we have to leave hands off. We can't touch it, we can't move it, we're stuck. Okay? So that's the issue there. Does this make sense? All right. Let's see what time it is. Here's another sequence of allocation. So A, B, C, D. Notice we get 3 1 kilobyte chunks and then a 2 kilobyte chunk, and then we free C, and then we free B. All right? Now we have this interesting situation where we have 2 chunks of memory that are now available for use, and they are adjacent to each other. Should the allocator be able to satisfy another 2 kilobyte allocation request? Yes, right? We'd like an allocator that can do that. Now, unfortunately, that means that the allocator has to be clever enough to know when 2 free blocks are adjacent to each other. So we call this coalescing. And if an allocator is incapable of identifying and coalescing adjacent free blocks, then we have false fragmentation, i.e., the allocator thinks that it's fragmented, but it isn't really. It's just dumb. Okay? So we'd like an allocator that knows how to deal with this as well. And like I say here on the bottom of the slide, since this is a common scenario, we'd like coalescing to be fast as well. And there are strategies for doing that quickly. Okay? Everybody with me? All right, last thing to talk about. We have 5 whole minutes to talk about this, which makes me glad, because data alignment is a complicated thing. A few of you have already asked me questions about data alignment, and I'm glad that you know about it. Data alignment is actually a really important concept in systems. Okay? We've talked about memory, and we've said, hey, we've got this giant array of bytes. It can be up to 256 terabytes because we have 48 bits of address. Aren't we awesome? And so we think of memory as an array of bytes, that we can access any byte. We can access 2 bytes together. We can access 4 bytes, 8 bytes. We're just awesome. Okay? The problem is the processor has a data bus. Remember, we've talked about, doing 64-bit processors this term. So 64 bits of data bus, which means we can read and write 8 bytes at a time. Okay? The thing is that the hardware always reads 8 bytes at a time. It always writes 8 bytes at a time. Okay? So if we have a processor that's reading and writing 8 bytes at a time, we need memory that's accessed in chunks of 8 bytes. Okay? We have to have that so that they can talk to each other at full bus width. Okay? So as an example, for our x86 systems that are 64-bit, we have a memory that looks like this. Chunk 0 has 8 bytes in it. Chunk 1 has 8 bytes in it, and so forth. So those memory cells actually hold 8 bytes. Now, you're always interacting with these 8-byte cells, but the nice thing about the memory is that you can say, here's a bit mask saying which bytes I actually care about reading or writing. So if you want to do that 1-byte access, you can just say, set the bit for that 1 byte and access it. And that's how you can sort of fake that you're accessing only 1 byte, even though you're reading and writing 8 bytes at a time. Okay? So we have abstractions, even in the hardware. The processor is presenting to us, the programmer, an abstraction that I can read and write individual bytes. And it's like, yes, you can, but behind the scenes, I've got to be interacting with the memory in 8-byte chunks. Everybody got that? Okay, this is really important. Yeah. Okay, so here's what memory kind of really looks like. Okay, the boxes will contain individual byte addresses, and then the number to the left of each cell is the actual cell address. So you can see cell 0, cell 1, cell 2, cell 3, blah, blah, blah. Okay? So when a program says, here's the address I want to interact with, the processor does a little bit of translation. Now, it's a really simple translation. I want to write a value to byte address 16 hex. Okay? Well, somehow the processor needs to figure out which 8-byte chunk it's interacting with. Turns out that's really easy. All it needs to do is throw away the low 3 bits on the address. Because the low 3 bits tell it which byte inside the cell I'm accessing. Okay? So the CPU might do something like this. Write this big 8-byte value, 000000, blah, 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 FF00. So it's putting a byte into the 7th position, and it says, I want to do that to memory cell 2. Okay? So this is what the processor is doing behind the scenes. This is nice. We don't have to think about this. I hate thinking about it every time I teach this class. I get to this slide, I'm like, oh, I got to explain this again. But thankfully, we don't have to think about this because the processor's taking care of all of it for us. Everybody got that? All right. So what happens if a program decides to access 8 bytes and it spans multiple memory cells? How many memory accesses do we do? More than 1. In this case, we're doing 2. Because you can see that it has to pull the first 2 bytes from the first memory cell that this thing is living in, and then it has to pull the rest of the bytes from the second cell that it falls into. So read memory cell at address 0, keep only bytes 7 and 8. Read memory cell at address 1, keep the bottom 6 bytes, and then put them together for us. Annoying, huh? Thankfully, the processor does all of this for us. Like I told you, x86 will walk your dog. It is that clever of a processor. But not every processor is. And so there are processors that just say, you know, you're not allowed to do this. Everything has to be in at most 1 memory cell. Okay, so it only supports aligned access. Okay? So you can see that the compiler and the memory allocator have to think about this as well. Okay? Any questions? All right, since we're out of time, what I'm going to do is just show you a few details here so you can look at that on your own. Nothing's complicated. If you've already gotten the basic idea, then you're set. You don't need to worry about it. But next time, we'll continue discussing explicit allocators and how they work.